Okay, our third QQT from Unit 4 is a scenario that we've seen before. I think it was Unit 1 or 2, where we've got a block being launched from a ramp. This time we're going to focus on the work done on the box. So just to refresh your memory, a box is pressed against a horizontal spring, compressing the spring from its relaxed length. The box is then released and the spring launches the box horizontally along a track that ends in a ramp as shown. The box has enough speed to leave the ramp. The box reaches a maximum vertical height. Assume there's negligible friction between the box and the track, and that air resistance is negligible. We got the spring constant. We've got X is the distance the spring is compressed. M is the mass of the box. Theta is the angle of the ramp. And H is the maximum height. So these variables make some sense here. The scenario is repeated using a box with greater mass. The spring is compressed the same distance. So how does the maximum height compare here? Okay, well, the answer is the maximum height is lower. Here's why. All right, so a larger mass, right? The energy stored by the spring is 1/2 kx squared. That's the same. Even with a higher mass isn't even in there. However, what that system does is convert that to kinetic energy, 1/2 mv squared. Now, with a higher mass, the kinetic energy will be the same, but the velocity will be lower, okay? And a lower launch speed from the spring is going to correlate to a lower launch speed from the ramp, and the y component of the y component of the velocity is what indicates the height, the maximum height for the block. So 2 points there. And again, I did write some formulas here. You would actually have to write the words. 1 point for indicating that a larger mass would result in the same amount of stored energy, but a lower initial speed of the box, and that the launch speed of the box is what drives the maximum height. So 1 point for that. So 2 points there. All right, point B, the students derive an equation for H, which may or may not be correct. Hopefully you guys are getting used to the scenario here. That's why we practice. Sine squared theta times kx squared over 2mg. Okay, may or may not be correct. Is this consistent with our statement from part A? What did we say in part A? What we said is if the mass increases, the height decreases. Let's see if this formula works. Mass is here in the denominator. So if the mass increases, the fraction decreases, and then the height decreases. So the answer is yes. All right. So 1 point for saying yes and for addressing the formula, and then 1 point for saying that since m is in the denominator, m increasing makes h decrease. So 2 points for part B. So hopefully this is going along well. Here we are, part C, D, E, and F are student 1 and student 2. Two students are discussing the work done on the system containing only the box. All right, so here's where I talked about like kind of having a note sheet here. I would do that. I would write system equals box only. No UG, right? No US, right? Only K, right? That's all we can discuss now, right? Student 1 says, at first the mechanical energy of the system increases because the spring does positive work on the system. Then the mechanical energy of the system increases again as the box travels up the ramp because the box's potential energy increases. Okay, the first statement is correct. At first, the mechanical energy of the system increases because the spring does positive work on the system. If the system's only the box, then yes, the spring is doing positive work on it and speeding it up. However, the second part is wrong. The mechanical energy of the system decreases actually as that box goes up the ramp because gravity's doing negative work on it, it's slowing it down. So C, the first statement is right. D, the second statement is wrong. All right, E and F is student 2. The mechanical energy of the system remains constant while the spring pushes the box because the work done on the box by the spring cancels the work done by the spring on the box, okay? Be careful of anything talking about work canceling out, all right? It's almost never correct. And even if it is, it's a weird way to say it. The mechanical energy of the system does not remain constant. We just decided in part one, the mechanical energy increases because the box is speeding up. So the second statement is wrong. I'm going to jump ahead to F there. Let's look at, the first statement is wrong. Let's look at the second statement. When the block is on the ramp, the mechanical energy of the system decreases because the box slows down. That is correct. Okay, remember the system is just the box. If the system were the block and the earth, then that second statement would be wrong. Mechanical energy would stay the same. But since the system is only the box, that's how that works out. So C, D, E, and F, 1 point each. All right, now part G. Does the mechanical energy of the box spring earth system, now we got all of it inside, okay? Does the mechanical energy of the whole system increase, decrease, or remain the same from the moment the spring is released until just before the box hits the ground, okay? So we have no friction between the block and the floor. We have no air resistance. So if we have box, spring, earth system together, all in one system, there are no external forces. So until it hits the ground, right? And they've specifically said right before it hits the ground, no external forces mean energy remains constant. So we need to justify our answer, okay? The total mechanical energy remains constant. When the spring is compressed, it's all spring potential energy. When the box launches, it's all kinetic energy. Some of the kinetic energy becomes gravitational potential energy while the box is going up. At the top of the ramp, it's all gravitational potential, at the top of the loop, it's all gravitational potential energy. And as it comes down, more and more kinetic energy. So 1 point for saying that the energy remains constant, 1 point for saying that initially there's spring potential, 1 point for saying finally it's all kinetic. So 3 points there. So part H says if air resistance were not negligible, how would that affect your answer to part G, if at all? So the answer is that air resistance would decrease the mechanical energy of the system. Okay, it would do outside work because we would have to, in order for it to remain constant, we would have to include the air in that. So 1 point for saying air resistance would decrease the total mechanical energy of the system. Finally, part I shows a graph with the vertical component of the velocity of the box as a function of time. The graph represents the entire area of the box is in the air from when the box is launched. How would the total area under the curve be different, if at all, if the ramp angle were increased, but still less than 90 degrees without changing the height of the end of the ramp? Okay, so we're going to launch from the same height, but it's a different angle. So the area under the curve means total displacement. Okay, the area under the curve of a velocity versus time graph means total displacement. Now, the total displacement of this box between when it's launched and when it hits the ground is simply the difference between the top of the ramp and the ground. It doesn't matter if it's going to go higher or lower because it's going to come back eventually. So the total displacement is going to be the same. The area under the curve means total displacement. Yes, it would go higher, but it still starts at the top of the ramp and ends up on the ground. So the area, the graph would certainly look different, but they didn't ask how the graph would look different. They just asked how the area under the curve would be different. So you get 1 point for saying the area would be the same, 1 point for saying the area equals vertical displacement, and 1 point for saying that since the box starts and it ends at the same place, the displacement would be the same. So 3 points for part I. And that's it for this question.